Professor Noe, I think you are muted.
Yeah.
Sorry for that. How about now?
Yeah.
It's good now.
All right, then. Cool. Yeah, so thank you very much for having me. And so I'll give you an overview of some of the things that we're doing on the interface of deep learning and physics, and basically go through a couple of different projects, and I'll kind of try to explain the physics problem and how it translates into a machine learning problem, and how machine learning can be used to somehow do something about the physics problem. And so in molecular physics, we are interested on one hand in understanding, and the other hand in possibly designing or improving certain processes involving molecules or materials. And there are, of course, a lot of possible applications there, because pretty much everything that you see around yourself, except for light, is made of molecules. So it's incredibly important in order to understand what things are made of and how the properties of materials, and also our ability to perhaps design drugs, so medication, to design functional materials such as solar cells, to influence how things get made. So catalysis is an important topic. So basically the speeding up of reactions that would otherwise be extremely slow. So all these are very important industrial applications, and also very challenging academic problems. And despite the fact that molecular science is such an old field in a way, I mean, chemistry is a very old field, we are still really far from understanding many of these molecular processes well, and also really far from being able to manipulate or being able to simulate them well. And a key problem there is simply that everything molecular is really small. So it's just a lot smaller than the wavelength of visible light. And because of that, we can usually not directly see anything that's the size of a molecule with an optical microscope. And therefore, we cannot simply look at what molecules are doing. So we always have to somehow use indirect methods in order to observe what's going on, and then somehow make inference about what actual process might have caused this observation experimentally, or alternatively do computer simulation and somehow try to understand from the computer simulation what's going on. But unfortunately, these computer simulations are, if they are supposed to be really accurate, super, super expensive. And so now if we're thinking about how we can bring machine learning or AI into the picture in order to help us, there are basically sort of two ways how you could do that. So if you think about a scientist working in the lab and doing some chemistry, so basically there are two things the scientist is doing. One, kind of making stuff, perhaps mixing certain chemicals, and on the other hand, take measurements, so make observations. And we can, on one hand, think about replacing part of what the scientist is doing by some sort of AI system. For example, a reinforcement learning system that is trained on some data, but then also interacts with a lab, which is somehow automated, and then improves its own knowledge about how certain things work in the lab, how certain reactions proceed, for example, if certain chemicals are prepared under particular conditions. Or alternatively, just forget about the lab and replace that with a computer, with a computational lab. And basically try to answer all the questions you might want to answer in the lab instead in the computer. And that's kind of the dream of theoretical chemistry in a way. Can be able to make kind of predictions involving molecules and compute properties of molecules with an accuracy that is at least as good as in real-world experiments. And unfortunately, we're very far away from that for most molecular properties, but we're kind of getting closer every year. And where we are good and where we are not so good depends a lot on the scale of what we are trying to observe. So for most molecular problems, it is such that we're actually looking at multi-scale phenomena. So of course we have small molecules and certain processes that happen in small molecules in isolation. For example, a small molecule in vacuum that is hit by photons. So we just interact with it by light, by shooting a laser light on it, and then we see perhaps emission of photons again that are somehow scattered by the molecule. That those are things we can do in the lab, but in reality, most interesting processes involving molecules are much more complicated than that, because in reality, maybe this molecule is in a solvent and there are many other molecules as well that are interacting with each other, or we're looking at the materials or a bulk material, or we are looking at something as complex as a biological cell where we have lots of very different molecules moving around and doing complicated things. And so usually we have like a multi-scale problem. And we're pretty good in making predictions about really small scales and really large scales. So really small scales, because there we can actually solve some fundamental equations like the Schrodinger equation with a very high accuracy. So before sort of the curse of dimensionality is starting to kick in. And large scales, because these systems are directly observable, and also at large scales, the thermal fluctuations of the atoms kind of average out and things become a lot more deterministic. And then we can do pretty good models with, for example, partial differential equation-based models or computational mechanics models, etc. But in between, it's hard because things are kind of too large for them to be solved directly with, trying to solve the Schrodinger equation directly. So we need to rely on models that are somehow built on more accurate calculations on smaller scales. And we somehow need to make sure that errors in these models don't accumulate in an uncontrolled fashion as we go higher in scale. But we are not yet where kind of the continuum limit kicks in and we can use like relatively simple deterministic equations. And so this is kind of the hard part, everything that's in this like white haze here. And we can, of course, so every year computers get faster every year, algorithms get better, and also machine learning is more and more used in order to improve these discovery methods or these analysis methods. And so by combining these, we can kind of push the boundary and get further and further into this region that's hard to resolve. And so now thinking about the physics and how do we get that together with machine learning? So when we build AI or machine learning models for molecules, or generally when we build any AI or machine learning model, we in principle have to answer two questions. So what is the optimization problem? Because usually we're solving an optimization problem, we're minimizing or maximizing something. And what is the learning structure? So what is the algorithmic structure that has some set of parameters that we are optimizing over? And now there's something special in physics, namely that usually we know a lot about the problem before we even start working on it. So usually we have some sort of physical theory which tells us something about the structure of the equations that we are trying to solve, which may have symmetries in them, there may be a certain principle that is obeyed in the limit that we have found the solution, perhaps a variational principle. So we can use that in order to define our optimization problem. Yeah, there might be symmetries or other constraints that the solution needs to satisfy in order to give the right physical answer. And these are all things we can use when designing a machine learning model. And in many cases, we actually really should use them in order to build models that make predictions that are, that have the right kind of behavior, let's say, that kind of fit in the in the physical framework in the right way. And so this is essentially what my work group has focused on, trying to take interesting physics problems, understanding what the physics tells us about kind of a machine learning model that would be suitable to address some of the computational problems, and then trying to build methods that do that. And I'll start with one example that's on electronic structure and quantum chemistry. And so this is essentially about the aim of solving the electronic Schrodinger equation. So on the top left here, you see the, not sure how I make this pointer visible. Well, anyway, that should work. So on the top left here, you see the electronic Schrodinger equation. So what this shows is basically, this is the so-called time stationary electronic Schrodinger equation. It's basically an eigenvalue problem. So we have an operator, h hat. And this operator is simply, it's kind of a sum of terms that basically determine how the electrons and the nuclei interact with each other. And mainly this is like electrostatic interaction. So electrons repel each other, and electrons and nuclei attract each other because they have opposite charges. And there's also another term in the Hamiltonian, which is called the kinetic energy operator. And that basically is the second derivative of the, it's just basically the second derivative, so the Laplace operator, which is applied on these functions in this eigenvalue equation. And the functions here, these psi functions, are functions that depend on the positions of all the electrons. So this R1 to Rn are positions of electrons. So for each of these, each position in this 3n-dimensional state space of electrons, this function has a value. And for now, we can assume this is a real valued function. In general, it will be a complex valued function, but for the problems we are looking at, we can assume it's just real valued. But it has a sign, so it can be positive or negative. And on the right-hand side, you also see this E. This is the eigenvalue, and this is an energy. So now if we solve this eigenvalue problem, so we find the eigenfunctions and the eigenvalues that solve this eigenvalue equation for a given Hamiltonian. And by the way, the Hamiltonian is just a simple object which is given from the beginning. So that's kind of easy to get. But the solving it is hard. So then, if we can solve it, then these eigenfunctions basically tell us something about the probability of finding electrons anywhere in space. And actually the square of this function, so psi square, which is then an unsigned function, so just a positive function, that is the probability density to find a certain electron configuration. It's a function over 3n-dimensional space. So there's a high-dimensional probability density. And this energy E, that is basically telling us something about the stability of this quantum state. And because it's an eigenvalue equation, it has many solutions. So it has many pairs of eigenfunctions and eigenvalues. And each of those is a quantum state. So the state with the lowest energy, that's called the ground state. So mostly the electrons around a given molecule will be found in that state. But there's also a certain probability of finding the other states with higher energies. And these are called excited states. And these are relevant, for example, when you interact with a molecule with some form of energy, when you shoot laser light at it, when you have high temperatures, etc. So then there's a probability for the electrons to populate these higher states. And because in these higher states, there will be other eigenfunctions, that means there will be other probability densities to find electrons somewhere. So the electron configurations kind of shift around. And because of this, you can basically cause the molecule to adopt different states and different configurations if you activate these excited states. Okay, but let's focus on the ground state first. So we just want to find the lowest lying eigenvalue and eigenfunction of an eigenvalue equation. Okay, that sounds easy, but unfortunately it's not. And there are two reasons for that. One is because it's a high dimensional problem. So we want to find an eigenfunction over a 3n dimensional space. So it's not really possible to do that by just discretizing the space and forming just a matrix, because if you have more than 3 dimensions, basically discretization becomes really hard. And maybe you can think of using some sort of sparse grids and go to like 10, 20 dimensions. But if you're in like 100 or 1,000 dimensions, even these methods break down. So that's one problem. And then another problem, and I'll come to that in a minute, is that actually there's a constraint, an additional constraint that the solution needs to obey. And this constraint is a combinatorial constraint. And that's what makes the solution of the Schrodinger equation really hard. And on the right-hand side, you see a diagram of essentially different methods. These are all quantum chemistry methods, which try to solve this equation, just try to find this first eigenvalue and eigenfunction of this equation using different simplifications, different levels of simplification. And you can see that the more accurate you try to be, the more expensive the method becomes. And it becomes very quickly really, really expensive in terms of the number of electrons n. So you can easily have methods that scale as n to the 6, n to the 7, n to the 10, or even exponential in n, if you want to be really accurate in approximating the solution. But of course, in practice, and this problem is NP hard, so this is known. But in practice, of course, even if a problem is NP hard, it can often be solved with high accuracy in many practically relevant instances. And then this is what's interesting. So what we're interested in is finding like kind of good approximation that work most of the time and have kind of a good trade-off between accuracy and cost. And there's one famous approximation, which is called density functional theory, which is by far the most widely used quantum chemistry method, because it has a very good trade-off between being quite accurate and quite cheap. And so we believe that there's another such method which has a really good trade-off, but that needs to use some form of machine learning. And we believe this is Quantum Monte Carlo with some form of machine learning that makes it powerful enough to approximate essentially complicated functions in high dimensions. Okay, and so for this, to get to this solution, we first need to turn the problem into a machine learning formulation. How do we do that? How do we turn an eigenvalue problem, the solution of the eigenvalue problem in high dimensions, into a machine learning problem? Well, we need a formulation where we can somehow minimize or maximize something. And with eigenvalue problems, one approach to do that is to use a variational formulation. And in this case, this is actually, so the operator here, the Hamiltonian operator, is self-adjoint. So it's like in matrix form, it's a symmetric matrix. And in this case, we can actually use a variational principle to approximate the eigenvalues. And as we approximate the eigenvalues, we also approximate the eigenvector, the eigenfunction. And so this is what we will be using. So we formulate the search for the ground state eigenvalue as a minimization problem over a functional which depends on an ansatz for the wave function. So we replace the exact wave function that we don't know by some sort of ansatz function, and we will represent this wave function with a neural network. And then we need to compute something, so some functional of this neural network function, which gives us an upper bound to the eigenvalue, and we will minimize that. And in the limit that we found the global minimum, we know we have also found the exact eigenfunction. So this is the machine learning problem. And this was actually in terms of using machine learning for this was actually pioneered by Giuseppe Caleo and Matthias Troja in this famous science paper that they wrote in 2017, where they used actually restricted Boltzmann machines to represent Hamiltonians, quantum Hamiltonians on lattices. So that's a quite different, and also so-called bosonic lattices. That's a quite different problem from what we want to solve, because we are interested in molecules. Molecules have electrons. Electrons are not bosons, but fermions, and they are in continuous space, not in some discrete lattice space. But the principal idea is similar. And so if we follow this variational principle and then translate this into and we use a neural network to represent the wave function, then we naturally get something that is called Quantum Monte Carlo. And that's a method that is quite well known in quantum chemistry. And so basically in Quantum Monte Carlo, we do the following. We write the expression for this functional, for this energy functional, as an expectation value. It is actually written as an integral over psi multiplied with h applied to psi, integrated over all configurations of electrons. This is something we can generally not solve, because we cannot generally integrate this expression over a high-dimensional space over arbitrary functions. But we can replace it always by a numerical approximation to the integral. And we use Monte Carlo in order to sample this integral. And it turns out we can rewrite the integral in a way that we basically sample with respect to the probability density psi square. So the probability density of finding electrons in this 3n-dimensional space. And then for each sample, we have to compute the quantity which is on the right, this so-called local energy, which is h psi divided by psi. And whenever we have a neural network or any kind of function that allows us to compute the value of psi for a given set of electron positions, we can compute this quantity. Is there a question or no? Okay, sorry. So this is basically what we do. This is Quantum Monte Carlo. So we have a neural network which represents the wave function. In every iteration, we will generate samples of electron positions, as you see in the picture below. So these are really, the electrons are treated as particles in 3n-dimensional space, and we have n of them. And we sample their position according to our current belief of what psi square is. And that's a way to generate samples for our mini batch. And then we take our mini batch and we compute this local energy on that mini batch. And that gives us a value for the loss function. And then we just backpropagate this loss function through the neural network, change the parameters a little, and repeat.
I think Kyle had a question. No, Kyle? You muted.
No question.
Oh, okay, sorry.
But feel free to ask questions in between.
Could I ask a question?
Sure.
Yeah. Do you have to? This is totally outside of my domain of expertise. So do you have to be careful about the specific form for the neural network that represents psi, so that this like upper bound holds? And if so, are you going to? Okay.
Exactly.
Are you going to talk about that? Or okay,
that's where all the difficulty comes from, actually, because if you would just minimize over functions in 3n space, it would be a lot easier. And this is exactly this difference between bosons and fermions that I was talking about before. So basically, fermions, electrons, for example, are fermions. Are particles that have a spin, and they can be spin up and spin down. You can just imagine this as some sort of color or whatever flavor that the particle has, and their behavior changes also as a function of this spin. So actually, this function psi is not only a function of the coordinates, but also of the spins. And specifically, this spin introduces a constraint to the solution, which is exchange antisymmetry. So electrons that have the same spin. So let's say we have n electrons and half of them must spin up and half of them must spin down. That's a good enough assumption for now. Now all the electrons that have the same spin that are in the spin up bucket, let's say, so they have some positions and each of them have a spin up. And now if I exchange two of these electrons, then the wave function, this psi function, should change sign. So it should be antisymmetric with respect to exchange of the electrons in the same spin set. And this, of course, the wave function itself is essentially just a mathematical object. It's not directly observable. So the sign of the function is not directly something that we can observe. But of course, this has a huge consequence because the square of the wave function is the probability to find electrons somewhere. And because of this antisymmetry, it means these wave functions will go through zero at certain places in certain hypersurfaces, basically. And wherever this happens, the probability of finding electrons is also zero. So this sign change of the wave function basically creates the entire structure of the probability density. It basically gives rise to kind of like modes modes of the probability density that are surrounded by zero probability. And this unfortunately makes this function extremely ugly. And also this exchange argument, this is what's introducing the combinatorial complexity, because there are exponentially many ways to exchange electrons, exponentially in n. And because of this reason, approximations that try to be extremely accurate are actually exponentially hard. So, okay, so how do we, first of all, how do we deal with this? We must introduce this constraint in our solution, because if we would not, we would inadmissibly relax the solution, right? Then we would find probably an energy which is too low and get an unphysical solution. So that wouldn't really help us. So a practical way to introduce antisymmetry, which is by far the most used approach in quantum chemistry, is to use matrix determinants, because matrix determinants also conveniently have the same property, that they are antisymmetric, meaning if we exchange two rows or two columns, the sign changes as well. And so if we somehow build a matrix where either the rows or the columns represent electrons, then we have a mathematical object that has the same properties, and we can use these matrix determinants as building blocks for our solution, as sort of terms to build up an expansion with which we represent the wave function. And that's so-called Slater determinants, and this is the standard approach in quantum chemistry. So how does that usually work? So usually we have our n electrons. We have a set of functions, and these are usually fixed functions, basis functions, that are used as building blocks to represent our solution, our wave function. And we have a large set of functions, and we take n of those functions, we select n of those functions, and we evaluate them at the electron positions. And we do that for all pairs of functions and electrons, and then we write the results in this n by n Slater matrix. Now we take the determinant of this matrix, and then this is an ansatz, and kind of like a very simple approximation to the wave function. Usually what we do in practice is that actually every function phi here that enters this matrix is itself a linear combination of simpler functions, and then it is these coefficients that we optimize over. All right, so if we do this with one determinant only, this is the so-called Hartree-Fock method. And this is a sort of the simplest approximation to the solution of the electronic structure problem, of this eigenvalue problem. And it's actually not too bad, but in many cases it's not quantitatively good. It's often kind of qualitatively good. It kind of gives a meaningful shape of the function. It gives you an idea where the electrons are roughly located, etc. But it doesn't give you a very good approximation of the eigenvalue. And if you want to get better, basically you have to add more determinants, because there are now exponentially many determinants that you could build by selecting other sets of n functions from your set of functions. And again, this is where the exponential scaling in high accuracy quantum chemistry method comes from. But at least we have the right structure. We have the right sort of functions that we are searching over. Okay, so now what do we do with deep learning? So there's a trick that works really nice together with machine learning. And this trick is called backflow. Again, this is not a new trick. This has been invented by the Quantum Monte Carlo community maybe 20 years ago or so. But so far, it has not really been put to a lot of use. And the reason for that is, in order to really benefit from this trick, we need actually very powerful function approximators. And we didn't really have that until recently. Okay, so what is this backflow? So the idea is as follows. So we take our n electrons and we insert them into a function, and this a multivariate function, and this multivariate function will again have 3n coordinates as an output. Yeah, 3n coordinates go in, 3n coordinates come out. The coordinates that come out again represent some sort of particles. Let's call them pseudo particles or pseudo electrons. They're not really physical particles, but the idea is that these are sort of particles that have, because they have been transformed by this many-body function, they have some information about the global configuration of all particles. Right? So initially, every particle only knows about itself. And after this functional transformation, every particle has somehow experienced the presence of all the other particles as well. And now we take these new particles, these new pseudo particle coordinates, and we enter our simple functions. And now the hope is that we are much more expressive because we have multi-body information in the input. Alternatively to this view of changing with particle positions, you can also say we don't take fixed functions, but we actually change our functions with some sort of neural network function. And it turns out that these two views are actually equivalent. So you can essentially express it one way or the other way. And actually in practice, what we do is the second approach. So if you look at the ansatz in the top right, so actually what you see here is we still have our matrix determinants. Let me just show you the difference to before. So before we had determinants of fixed functions, and now we have and also these are functions of single particles usually. This Ri are individual electron positions. And now we multiply each of those with a multi-body function, which depends on all the electrons. And also it's a parametric function. So this is a neural network function, this f mu I. And the only thing we really need to take care of is that our neural network function is exchange equivariant. So meaning if we exchange the positions of two electrons, then the entries of this F vector, which goes into our matrix, also exchanges, such that we still have this property that exchanging two electrons corresponds to exchanging two rows in the matrix. And therefore the matrix can still be used to represent an antisymmetric function. Okay, so that's the main trick really. And then we also have like an additional function that we multiply with this whole expression. And this is a symmetric function. So it's invariant under exchange of electrons. And that's just because we can do it, right? We can always take an antisymmetric function and multiply it with a symmetric function, and it's still an antisymmetric function. And it just gives us some extra expressivity. Fundamentally, we don't need to do it. Fundamentally, it's clear that this antisymmetric part of the expression should be enough, but in practice, it just helps to get some extra flexibility here. And so this is the overall learning system. And so it looks quite complicated, but basically everything that you see in the top right, all of this orange part, that's just the neural network part, which represents the so-called backflow, and this Jastrow factor, which Jastrow factor is this symmetric part. And this is basically a graph neural net. So we treat the electrons and the nuclei as nodes in the graph, and we let them interact with message passing. And the graph, neural network is built such that it's equivariant with respect to exchange of electrons. And this produces basically the neural network functions for the backflow and the Jastrow. And then we have some other stuff here in green, and this is basically all fixed, and it's built such that the physics is respected. So Hartree-Fock just means we start, let me go back here, these 5 functions here are functions that we start with, and then we modify them with neural network functions. And we do that in such a way that when we begin training the neural network, it actually outputs just constant 1, so that we always start with these fixed functions. And these fixed functions are actually obtained by a standard quantum chemistry calculation called Hartree-Fock, or some variant of Hartree-Fock. So that just makes sure we start from a reasonable starting point. And then there's another box here, which is called electronic cusps. And this is kind of a special thing, so there's an extra piece of physics that we know, and that has to do with asymptotics. So as 2 electrons approach each other, or an electron approaches a nucleus, so in those limits, the probability density to find electrons in these limits is actually 0, or it goes to 0. But we know something about the asymptotic behavior of the wave function psi as it approaches this limit. And it is useful to just design our neural network such that it has the same asymptotics, that even before we do any training at all, our function will have the same asymptotic behavior. And that really helps the training as well, because as I said, the probability to find electrons in these limits is small. So we will very rarely sample a state which is close to that limit. And then if we're completely naive about the value of the function, we get like a very poor training signal. We get like these spikes in our gradients, basically. And that really ruins the training of the neural network. So it helps a lot to just kind of build the asymptotics in. And that's basically it. So this is the neural network, which represents the wave function. And then we have this Monte Carlo training scheme around it. So we take the wave function. The wave function represents also the probability density to find electrons. Then we do some Monte Carlo, basically, in order to sample electrons from this probability density. That generates our batch. We compute our loss function, backpropagate, update the parameters, and repeat. So it's completely unsupervised, or self-supervised, if you like. So you only specify the Hamiltonian, and the neural network kind of generates its own training data, and by minimizing the energy, it trains itself in a way. So we don't need any additional data. Okay, some results. So basically, what we do here is we use only one or a couple of matrix determinant in the neural network. Let me just go back to the scheme. So in the end, you have these matrix determinants, which make the whole function antisymmetric. And as I said before, in these classical quantum chemistry methods, you need to add more determinants to reach higher accuracy. And the really accurate methods can use millions of determinants, right? Millions of determinants of pretty large matrices. So that's getting really, really expensive. And instead of that, we just use 1 or maybe 10 determinants, so something on this order, let's say 10. So we kind of have a budget of determinants, but because we can train the backflow, each of those determinants can be quite expressive. And that's basically the bet here. We want to get away with very few determinants. We don't want to get into this exponential scaling in the number of determinants. Instead of that, we're kind of searching over an exponentially large number of continuous functions which produce the entries of the determinants, which is not obvious if this is like a better deal, but at least it's something that we kind of know that neural networks are good at. So it's intuitively seems to make sense. And indeed, we can get very high accuracy solutions to these small molecules with 2 orders of magnitude or even more or even less Slater determinants compared to, you know, good quantum chemistry methods that use standard approaches, let's say.
Can the determinants be computed in parallel? It does seem like there's a computation angle to this.
I mean, we computed on the GPU, so I'm sure it's parallelized
Already.
in that sense.
So
Yeah.
what's the bottleneck then? The fact that there's many.
It's still, I did the backpropagation through the determinant. That's the most expensive part. Yeah.
Okay.
That's actually the most expensive part. There's also so in the Hamilton, so when we compute these local energies here, so the loss function basically, that involves the Hamiltonian. And the Hamiltonian has this second derivative, this Laplace operator. So this would become like a third derivative if we did standard backprop, which is like really painful. But there's actually a trick to rewrite this. It's basically the same trick as the reinforced trick, to rewrite this in such a way that we only need second derivatives. But it's still second derivatives over matrix determinant. So that is expensive. But practically the method scales as n to the power of 3. And that's cheap for quantum chemistry. And n to the 3 is like really cheap.
Same as DFT.
Is about the same as DFT. Again, in DFT, it depends exactly which version of DFT. So there are versions of DFT that are like n to the 4.
Oh, okay.
But roughly the same, but with a much bigger prefactor.
Good.
Because we're using a neural network to evaluate the wave function. So this is very expensive each time we call it. But it's hopefully much higher accuracy than DFT. And so it scales much, much better than other high accuracy quantum methods. So eventually for a big enough n, this starts to make sense.
Yeah.
Let me give another example. So here is kind of the next version of this network. And this next version actually does not only compute the ground state, but actually multiple quantum states. So also some excited states. And it does that by having essentially different neural networks representing each of these states. And additionally, we have some orthogonality constraints between the wave functions represented by each network. And in the lower part of the picture, you see the benzene molecule. So that's still a fairly small molecule. It has 42 electrons. So n equals 42. And on the right, you see a table for the kind of the node hours, so the computational cost of different quantum chemistry methods. So you can see the acronyms get really cryptic because people combine all kinds of ideas, and then you get these really long, weird expressions like ASFCI, QMC. And you can see that how the number of node hours really explodes for this fairly small molecule. And then as you go from 42 electrons to say 100 electrons, well, then basically you enter a regime where most of these methods are just completely impossible. Right. So this starts to pay off quickly if you really want high accuracy solutions beyond a certain n. And so the aim of this method is really that because we have a neural network that basically learns the solutions for a given Hamiltonian, this method is very flexible. So, and actually for all the examples shown here, we're using the same neural network. So we're not kind of specializing it for particular molecules. And that's really a strength compared to most quantum chemistry methods, where you additionally have to make certain choices in order to get good results for a particular molecule. So you have to have a lot of intuition. And this still works for most molecules if you combine them with a good quantum chemist. But as soon as you start using Hamiltonians that are kind of unusual, and you can easily get unusual Hamiltonians if you don't only have a molecule, but you have a molecule which is interacting with light. So then you have electron-photon coupling, or you have it interact with lattice vibrations in a material. So then you have electron-phonon coupling. And so then you get extra terms in your Hamiltonian that are easy to write down, but then you're immediately outside the range of where you have standard solutions and standard software packages that work well. And it's very difficult to get an even approximate solution. And then it's really convenient if you have such a kind of a black box solver, then you can just tell, this is the Hamiltonian, find a solution, and it optimizes a neural network function, and it finds a reasonable solution. So I think this is where the most benefit of these methods are, that we can actually start to explore regimes of quantum chemistry that we couldn't really explore so far.
Just in terms of assessing accuracy, and like, how do you get ground truth for these models? Like, as in the middle panel of the bottom row, like, should I be comparing PauliNet to the experiment, or should I have been looking at it relative to like, some of these more expensive methods? Yeah, like how do you like? Yeah, so it looks like in this panel, like DFT is actually, I don't know, it looks kind of like it's closer to the experiment, but relative to PauliNet. So yeah, maybe you could elaborate more on like kind of how you validate PauliNet's performance.
Okay, so I mean, in general, so PauliNet is like some other methods, not all other quantum chemistry methods, is a variational method. So we know we find an upper bound to the energy. And so for example, DFT is not. So with DFT, you can get energy that is too low, that's possible. And so first of all, you can compare it with other variational methods. So for these small molecules on the left, these diatomic molecules here, basically we can compute exact results. I mean, not exact, but you know, exact up to a certain number of digits that we don't really care about. So there we have a ground truth that is good enough, basically. And then we can also always compare to this ground truth, and then ask the question, you know, with the kind of scaling that we have, O to the power of n to the power of 3, how do we do compared to DFT, which has a similar scaling behavior? But also for something like this cyclobutadiene molecule here on the right, we have pretty reliable experimental results, and we have similar results with expensive quantum methods, and we get very different results with cheaper methods. So here we see that if we get like in a similar ballpark, like experiments and expensive methods with PauliNet, we're probably good. But then there are cases like these excitation energies. The excitation energy is the difference between the energy of the ground state and the first excited state, in this case for benzene. So that's what's shown here in this bar with green and blue colors. So there it gets a little bit fishy, because actually, as you said, there's certain experimental value, and actually, like, depending on which experiment you do, there will be like a range of different values. And then you are in the same range with DFT and with coupled cluster, which is actually a kind of a better method than DFT. And with PauliNet, we're kind of in the coupled cluster range. So here, honestly, we don't know. The only thing that we know here is we're kind of in the same range as most methods. But we're much cheaper than the high accuracy methods. So, but it's tricky. I mean, even getting accurate experimental methods values here is hard. Okay, I'm not doing so well with time, am I?
Oh, this is great.
All right. Okay, let me, how do I do this? Let me skip over this part, at least for now. We can come, well, let me give the motivation part and then skip to the next part. So now we're interested at another scale of macromolecules, or at least molecules with many atoms, or molecular systems with many atoms that are moving in time and space. And so what you see here are the thermal fluctuations of a protein molecule. So this is from a molecular dynamics simulation, but this gives, I think, a realistic picture of what the molecule does in the course of something like 1 millisecond. So you see the timer here in the middle, counting milliseconds. And on left and right, you see just two different views of the same protein molecule. And you see as the protein changes its configuration over time. So it's very dynamic and the atoms are wobbling around. And this is only due to thermal noise, basically, just due to temperature, finite temperature. And what you see in the middle is a so-called Markov state model. So that's basically just, we have kind of divided the state space of the molecule. So there's 3 n-dimensional, high-dimensional state space into sets. And what you see here is that whenever the molecule adopts a certain structure, it's in one of these sets. And we have built, or actually the authors of this paper here, which is a different group, has built a Markov chain model where you basically predict the dynamics of the molecule by having a transition probability between these states. Okay, and so in practice, when we compute properties for a molecule such as this, we're usually interested in computing statistical averages. So for example, the probability of a protein to be folded, or the probability of a protein to bind a certain drug molecule, which is needed to compute the kind of the efficacy of this drug. So how well does this drug inhibit the function of a certain protein? These are all statistical averages. So there are some integrals over all possible states that this protein molecule could be in, weighted with their probability density, multiplied with some quantity that we're interested to average. And the probability density that we want to sample over can usually be expressed as e to the minus u, and u is some energy. And this energy, again, is a kind of a long and complicated function. It could be a neural network function, or it could be a classical energy model for the molecule. And it usually includes all the interactions between all atoms. And it could be pairwise interactions, or it could be higher body interactions. So this is basically, you can imagine this to be a very long sum of many, many terms in which particles interact. So every single time we evaluate this function, it's expensive. And now, unfortunately, we have to evaluate this function many, many times in order to sample this integral. So first, we cannot usually solve it analytically, so we have to sample it again using some sort of Monte Carlo or molecular dynamics methods. And when we do this, for example, for these molecules here, Barnase and Bar-star, these are 2 small proteins. They're much larger proteins than that. If we also add the solvent, then we have about 100,000 particles. And all of these particles interact at least pairwise. So everyone with everyone else, and possibly higher body interactions as well. So our function has like millions or billions of terms. Okay. Now we want to sample this function, this energy function, or we want to sample e to the minus of this energy function. And one approach to do this is molecular dynamics simulation. It's basically it's a Markov chain Monte Carlo method. And so when we do this, it takes us about 1 week of GPU time to simulate 1 microsecond.
What?
but it unfortunately takes us about 50 microseconds to observe a single binding event of these two proteins, which would be like a GPU year, or a million GPU years to observe a single dissociation event, just for this one system. So this is completely unfeasible, right? And so, of course, there's molecular dynamics is also a field that is maybe 70 years old. So people have known about this problem for a very long time and have developed a lot of strategies to overcome it. And they're roughly characterized as enhanced sampling methods. And there's a whole zoo of methods. Like you find a zoo of methods in quantum chemistry, you find a zoo of methods in enhanced sampling, which are basically tricks to somehow speed up this process. So if I know what is the process that I want to sample, such as binding, unbinding, I can try to somehow bias this particular process, like a particular direction in this 3n-dimensional state space, and try to make it happen faster. And I know that I'm changing my probability density that I'm sampling when I'm doing that, but I also know how I'm changing it, because I can quantify my bias, and then I can use this knowledge to unbias my sample. So that's roughly the idea that most enhanced sampling methods follow. But in order to apply this, I have to know a lot already. So I have to already know what is the process that I want to sample, and I have to be able to kind of give a direction in which I want to sample, along which I want to sample. Mm-hmm. And this is often called a collective coordinate or a reaction coordinate. Because what it really is, it's kind of a path in this 3n-dimensional space. So out of all the many, many dimensions in which I can move, I'm focusing on one particular path. Okay, and in many cases, it's just really difficult to define such a path. And so moving forward, so we have thought about, can we somehow use generative learning, so generative deep learning, in order to help with this? And so the idea is the following. We know the probability density that we want to sample from. So that should somehow make the problem easier. So somehow it should be, because we already know the function defining the probability density, it should be easier than just having to make like tiny Monte Carlo steps. We just have to be able to train a machinery to somehow sample from that function. And so the idea is to use generative deep learning. And so generally the idea is, let's take a neural network, take noise or some random variables that are easy to sample from as an input, and then somehow modify the neural network such that it generates samples that are like the distribution that we're interested in. For example, photos of celebrities. And this is, as you know, something that works quite well for photos of celebrities, at least. And here are some samples from StyleGAN 2. And so basically, we want to adopt this trick in statistical mechanics as well. And because we know the probability density that we want to sample, we're really interested in exact likelihood methods. So methods for which we can not only generate the samples, but we can also compute the likelihood that the network will generate the sample. Because then we can actually compare this probability density of generating the sample with the probability density that we expect at this point. And we can try to minimize the probability distance between the two, such as the Kullback-Leibler divergence, for example. That's the easiest that you could think of. So one candidate here is normalizing flows, which are invertible transformations, invertible trainable transformations, for example, using neural networks. And because they're invertible, we can write down the transformation of random variables rule. So we can compute the probability density of the output of the neural network given the probability density of the input, which is something we can control. and the determinant of the Jacobian of the neural network, which again is something that we can compute for certain neural networks. Well, we can compute efficiently sometimes.
Is that what motivated the choice of a flow out of all generative models? Okay.
Precisely.
The likelihood is exactly tractable.
Exactly.
Okay.
That's the point, yeah. So, and then we can also combine this flow with some sort of reweighting technique, some sort of statistical mechanics technique, which takes the flow density and just modifies it a little bit to the exact density. And we do this really because in physics, it's very important to get unbiased estimates. So really, we want to have something which is asymptotically unbiased. So we're willing to accept a higher variance and sample longer, but we want something that if we sample long enough gives us kind of the exact answer. So in this kind of variance bias trade-off that you typically have in machine learning, physicists are really interested in zero bias, and possibly high variance. So because of this, we do reweighting. And then the combination of a flow and reweighting, that's basically what we call a Boltzmann generator. Mm-hmm. All right, so how can we train this Boltzmann generator? Well, because it's a flow and we can evaluate the flow backward and forward, we can train it in both directions, really. So the natural direction is we just generate inputs from a simple distribution, let's say a multivariate Gaussian, or some more informed distribution if we have that, push forward. And then we evaluate the Kullback-Leibler divergence with respect to the target density, the Boltzmann density, for example. And it turns out that this is this sort of expression, which is the minimization of an energy. And this is actually the energy function that we usually specify in the beginning before we do our molecular dynamics simulation. So this is sort of an input to the whole procedure. And the second part then is a term that involves the determinant of the Jacobian of the network. And this is basically an entropy term. So the first term is trying to minimize energy. The second term is trying to maximize entropy. And the overall thing is basically a minimization of a variational free energy. Mm-hmm. And we can also do the whole thing in the other direction. So if we have samples, possibly biased samples, but we have some idea of where we want to sample, we can take these samples and push backward through the flow and then try to make the resulting density similar to our prior density, to the multivariate Gaussian, for example. And in practice, we do both. So we start out with some data, but probably biased data and not completely representative data. And we start sampling from the Gaussian and we push in both directions and we minimize both terms. And so if we do this, for example, we can, so here's a very simple example of a dimer. You see this in the blue and red color. So these are basically two particles that are attached to each other with a tether. And this tether can either be short or long, but it doesn't like to be in between. So it's kind of bistable. It's either here or there. And going from here to there, it's a rare event. And additionally, there are all these solvent particles that can move around, these gray particles, and they're really filling up this box, and they're repulsive. So you can't really push them into each other without getting a high energy penalty. So because of that, whenever you want to open or close the tether, you have to shuffle the solvent particles around. So it's actually a complex move. It's a many body move whenever you want to do that. So it's not easy to come up with just a Monte Carlo move which tries to open or close the tether. And that's a typical situation that we have in molecular dynamics simulations. The rare events are usually complex motions where we have to move a lot of stuff around simultaneously. And it's really not clear how we would define a Monte Carlo move that would do a large step. And because of this, people are doing small steps which result in these molecular dynamic simulations doing tiny steps and taking forever to sample the rare events. And basically what this Boltzmann generator, these flows are trying to do is kind of how to learn to make big steps by leveraging the flow. And so in this example, we can basically sample the closed and open states, and also sample the relative probabilities of finding the system in closed and open, and do this for different temperatures. So the different green curves here are actually different temperatures. And so we can also do this with proteins. So here is a sample of like all the atoms in a protein generated at once with the flow. And so, yeah, I mean, currently we are basically pushing these techniques so that we can sample protein states efficiently, and we can do things like protein folding with these flows.
Sorry, Frank, can I interrupt you for a second to ask a question?
Sure, absolutely. I was actually going to finish.
I just wanted to clarify. I've also been reading on these like weighted ensemble methods, and so kind of like I'm trying to understand. So do you still have to define a progress coordinate with these flow models going back and forth, like the classical methods were doing?
I didn't quite understand that. Sorry.
You know, in the more traditional like weighted ensemble methods, like these enhanced sampling methods, you have to define a progress coordinate to sort of like measure progress on that particular, or like also called like a reaction coordinate, for example. Like, do you have to define that kind of axis with your flow methods? No.
No, you can define it. For example, if you're interested in the energy profile along a coordinate, then it is useful to do that, because maybe along this along this coordinate, you will have very low probability states. So if you just sample in equilibrium, you wouldn't populate them. But you don't have to. So you can actually compute energy differences between completely separate states. And that's really the advantage of the method. It's not as much a sampling method as a method that allows you to get the weights correct. So you can really start from two completely separate states. And because the Boltzmann generator basically, or the flow basically maps both of these parts of state space to the same reference state, which is this multivariate Gaussian. This is like a free energy diagram, basically.
Is the input, so it's trying to find a mapping between the input distribution and the output distribution, and is the input distribution like when, for example, the proteins are far away from each other, and like the output when they're like binded together, sort of, or like
so the input distribution is really a very simple. So in this example, we used a Gaussian distribution. So really, it's just particles that are in a cloud. It's just a particle cloud. So everything is, you know, every atom is independent. Everything is in a cloud, and they're completely uncoupled. And then as you go through the flow layers, basically the flow layers learn the coupling between the particles.
And the output distribution is all the possible conformations of the proteins, sort of in the space, including when they inbound and outbound.
All the possible conformations that the flow has learned to sample. Which again, this. So as I said, we train in both directions. So we have, on one hand, we generate from this Gaussian and then evaluate with respect to the energy. On the other hand, we start out with some guesses of relevant conformations, and we train in the other direction. And this is important as well. If we would not have that, we would generally just sample around a single conformation. So this method is really useful if you have some idea of certain states that are relevant, but you don't know what is their relative probability weight. And now you can combine this method with other methods that are more exploring things, like high temperature dynamics or metadynamics or something. And then as you explore new states, you can retrain your Boltzmann generator and then learn efficient sampling and reweighting at the same time. So these things are complementary.
Right. I might take it offline with you. Actually, I might send you an email afterwards.
Sure. That's fine. Yeah. So let me wrap up here. So we've also worked a little bit on stochastic normalizing flows. So that's introducing stochasticity into the network so that we don't only have to do invertible neural networks. And this invertibility constraint is quite a bit of a restriction to the architecture, of course. And we can actually relax this by replacing the network by something that's not exactly invertible anymore, but it still allows us to compute the probability of going forward and backward through the network. So basically we interspaced neural network layers with like Langevin dynamics or Monte Carlo steps. And we can still train this as a flow. And this has very interesting relationships to non-equilibrium statistical mechanics that in the interest of time, I won't go into it, but I just want to show you that you can actually, if you compare this to just sampling with a purely invertible neural network, and these are like just two-dimensional functions. So basically probability density is defined by images in 2D. So it's very low dimensional, but it's a very complicated probability density that paints the smiley or the dog. And if you just use a purely invertible neural network, like a real NVP network, then you see on the left what you get, and it's very messed up. If you only use Monte Carlo, and the way this works is we start at a point in the middle and we then do Metropolis Monte Carlo steps and we accept or reject with respect to the target density. Then, of course, eventually, if you sample long enough, you will get the exact correct distribution. But if you sample only for finite time, you will still be biased by the starting point. And that's what you see here in the second column. And if you just take these two things, like the real NVP network, which didn't work very well, and the few Monte Carlo steps, which weren't enough to sample the distribution, and you put those together and you train it as a stochastic normalizing flow, then this is what you get. So it works just way better. And it still allows you to compute exact probability weights for every sample that you train, even though you are not invertible anymore. So that's also an interesting direction, I think. And it's very closely related to these diffusion models that are now so popular and that are, for example, used in DALL-E. And yeah, so and with that, I'd like to finish. So sorry for going over time. And yeah, thanks to my group and funders and collaborators. And thank you for your attention.
Right. Thank you, Professor Noe, for a very interesting talk. Let's all give him a figurative round of applause. Yeah. So, I mean, I guess we do have some, maybe a little bit more time for extra questions if anybody has it. If not, I actually have a question. So back in the beginning of the talk, when we were talking about PolyNet, you mentioned that you had this equivariant transformation network to enhance the expressivity of your determinant expressions. Yeah, so, and I think you mentioned that it's a graph neural network, and you've set the structure of the network so that it has this equivariant property. Could you maybe give us a brief idea of how the structure of the network can guarantee this property?
So graph neural networks are usually exchange equivariant, and so is this. And one way to do this is basically, for example, you have vectors representing the particle positions, and then you do operations that compute some invariant property, and then you multiply this vector with this invariant function, and then it's still equivariant. And there are a number of ways to do that, but basically it's always such that if you exchange labels at the input, then you just basically get label exchange at the output or position exchange at the output.
I see.
And then another example, for example, is the gradient operation, right? The gradient operation is also equivariant. So if I compute an invariant function, so by doing, for example, an aggregation, a sum, let's say, I have a neural network, I compute a vector, I sum over it, so that's invariant with respect to the order in the input. Now I take the input and I compute the gradient of the output with respect to the input. And that gradient is again a vector, which is equivariant with the input. So it will exchange elements as I exchange it in the input.
I see. Yeah, so basically this is just your equivariant means just the exchange of any two pairs of variables.
Exactly. So as long as I do
for
kind of equivariant mathematical operations in the network, I can. It doesn't really have to do with something with the graph itself. It's just like the way these graph convolutions are defined is using these equivariant operations.
I had another question, Frank, if I may. So,
of course.
So going back to the second part of your talk on using the flow models, bidirectional flow models to learn particle distributions. So I'm trying to understand a bit kind of like the motivation and where you're coming from with that work. Is it like a method to be able to speed up molecular dynamics, or just to learn to sample conformation states, static conformation states of proteins, for example?
Yeah, static conformation states.
Static you don't do temporal dynamics,
correct.
So help me understand a bit more. Like, what's the use case? Why would you want to sample randomly like these conformation states of proteins?
I think in most cases you're actually interested in thermodynamic averages. So averages where the temporal order does not matter. Of course, that's not always.
I see, like in the Markov chain case where you said,
exactly.
I go what you mean when you were computing the time the process spends in a particular state or in a few particular states.
So for example, when you want to compute the efficacy of a drug, then what you can do in the molecular modeling world is to compute the binding affinity. So the probability that the drug will be bound versus not bound. And for that, I don't really need molecular dynamics because that's a static property.
Yeah. And sort of like and you can kind of do it normally with like a normal flow model, but the fact that you have it bidirectional flow, that helps with learning a better distribution, I suppose.
I mean, these normalizing flows are bidirectional.
Yes, exactly. They are. Yeah.
Well, I mean, of course, it depends what exactly I'm using. There are flow models that are not efficiently invertible, like autoregressive models, for example. Right?
Yeah.
So there's a bit of a trade-off. If I have something that's only efficiently something like the autoregressive model, may be more expressive, but is expensive to invert. So then maybe I can represent the function better, but because I cannot invert, I cannot train it in this reverse way, which is also actually called, so the first is called reverse KL, the second is called forward KL, but more likely.
This is, I'm trying to understand the contribution, because this is normally done with the normalizing flows, right? So your contribution was to apply to the particular problem, or did you actually end up changing the model itself?
So usually normalizing flows were trained with likelihood with the second version here. So what is special here is that in this physics problem, we have the energy. So the target density is given. And so instead of just learning from a distribution of samples, we actually want to learn to sample a target density. So it's a bit of a different problem setting from the traditional flow problems.
Oh, like yeah. So, so if you're sort of given the target density, but I suppose you don't know the normalizing constant, or you don't have a way to sample.
I don't have to. I mean, this will become a constant factor in the loss. So an additive constant in the loss. So I can just throw it away.
Yeah. Thank you. Got it.
You're welcome. And then, of course, the application as well. I mean, there are lots of practical tricks to make this work on molecules. I mean, I drastically simplified the discussion. To actually sample the structure here of a protein, you need to do a lot of tricks, like how you represent your coordinates, for example. This is not just using Cartesian coordinates.
Yeah. Thank you. Yeah.
I think we can stop it here, Peng-Ning.
Yeah, I think if there are no further questions, well,
Yep.
Thanks again to Noe for this very interesting presentation. And yeah,
absolutely.
This was amazing. Thank you so much.
Thank you for having me. It was a pleasure.
Bye.
Bye. See you soon, hopefully. Bye.